All right, so for number 14, we want to write an explicit formula for the G. Oops, let me unfreeze the board. All right, so what we talked about yesterday was we talked about geometric sequences. No, it's okay. So we talked about geometric sequences, and geometric sequences are a series of numbers that have a pattern. They're like an arithmetic sequence, but an arithmetic sequence, you're adding either a positive or negative number to each term. A geometric sequence, you're multiplying either a whole number or a fraction to each term. And so if we look, we have 32, 16, 8, 4. Right, so we're dividing by 2 each time. So with a geometric sequence, the pattern is in a multiplication format. So when you're dividing by 2, you're multiplying by what fraction? 1/2, yep. So here, so to get from each term, we're multiplying by 1/2. So let's write the explicit formula for this. So our pattern is a sub n equals the first term of our sequence times our r value, which is the number that we're multiplying by, and then it's n minus 1 because we're multiplying by the previous term. Taking the previous term. Yep. Yep. So building this one, we have our a sub n, so we want just a generic equation. So what's the first term of this equation? 32 times 1/2. Oh. And then n minus 1. So now it says determine the 9th term. So we can find, yeah, so 1, 2, already. We have our first term, second term, third term, fourth term. To find the 9th term with this pattern, it would take us a bit, right? So we come up with the explicit formula. And so we just, to find the 9th term, 32 times 1/2, and then n minus 1, so 9 minus 1, so that's 8. So we're going to take 32 times 1/2 to the 8th power. And then you set this one. Alright, so Michaela said she did the math and she got 1/8. And so if we followed this pattern, so this is 1, 2, 3, 4. So our 5th term would be 4 times 1/2, which is 2. Our 6th term would be 1. 7th term would be 1/2. 8th term would be 1/4. And then our 9th term would be 1/8. So this way was much faster than going through and solving individually. So, questions? So the explicit formula for a geometric sequence is a sub n equals 6 times 3 to the n minus 1. State the recursive formula for the sequence. Include the recursive formula in function notation. Alright, so what would be the formula written in function notation? So what's our recursive formula? So we have this geometric sequence. So let's go back. Well, what's our first term? We have 6, and what's our next term? So then, what are we doing each time? Multiplying by 3, so our next one 18, and then did you say 162? Alright, so now when it says recursive formula, what's it asking for? Yeah, so like if we were, let's go back and look from yesterday. So when it's asking for the recursive formula, number 7 and 8, we're dealing with the recursive formula. So each time we're writing that out like by individual terms. So instead of writing out as our explicit formula where you can put in any number for n, this one you need to know the previous number, right? So if we were to look at number 15, looking at just if you had to know the previous term. So this one, our recursive formula would be 6 times 3, right, to get our second term. And so then this would be our first term times our previous term. So 6 times whatever our previous term was. So right, n sub 1 is in this. So it would be 6 times whatever we have for f of n minus. So that's in our function notation to write that. We have n sub n equals our first term plus 3 times a sub n minus 1. So then, let me rewrite this. What did I do wrong with the function notation? It's 6, that's our first term, plus 3. So this is great if you're only looking for the first few terms, but when you start jumping around and wanting numbers and size, it gets a little tricky, right? But then you don't want to sit there and do 100 terms. So we have our first term plus n, we're multiplying by our previous term and adding that together, and then this one, our first term plus n multiplying 3 times our previous term. Alright, so how can you use the recursive formula for a geometric sequence to write an explicit formula? So this one, the recursive formula gives you your first term, and then it shows what you're multiplying each previous term by. And so that allows us then to write the explicit formula. So let's look at number 17. Write the explicit formula for each geometric sequence, then determine the sixth term of each sequence. So for number 17, what do we multiply each term by? We're multiplying by 5. And so 5, what letter of the explicit formula is that? So 5 is what we're multiplying by, right? So that's going to go into our R. And then a sub 1 is our first term. So what's the first term of our sequence? 1. So we're going to have 1 times 5 to the n minus 1. And And so let's check this. So if we want to find the first term of our sequence, we're going to put 1 in for n, right? So then we have 1 times 5 to the 1 minus 1, because we have an n here, and n is 1. So what's 5? What's 1 minus 1? 0. What's 5 to the 0 power? 1. And 1 times 1 is 1. So then if we want to find the second term, we put 2 in for n. We have n 2 minus 1, which is 1. So 5 to the 1 power is 5. 1 times 5 is 5. And the pattern keeps going. So the question says, what's the sixth term of the pattern? So we're going to put 6 in for 5. I mean 6 in for what letter? And my words aren't working with me today. Alright, so 6 minus 1 is 5. So 5 to the 5 power is, what is it? 3,125. And then we have that times 1. So 3,125. Alright, so now looking at 18, we have 48, negative 24, 12. Okay, so we're dividing by negative 2. Negative because we have a sign change, right? 48 divided by negative 2 is negative 24. Negative 24 divided by negative 2 is positive 12. But when we do an explicit formula, we don't divide. So when we're dividing by negative 2, we're really multiplying. So how would we write this explicit formula? Okay. So then what's the sixth term of that? There are two different numbers. All right, so let's check this out. So we're looking. Negative 1.5 or negative 3/2. And if we keep on check, if we look at this, 6. All right, so let's do. So we have 48. We have negative 24, positive 12. So the next one's going to be negative 6, and then we'll have positive 3, and then negative 1.5, 1, 2, 3, 4, 5, and that's our sixth term. So then, so in for n, we're putting 6, so we'll have 6 minus 1. Alright, so we all got that. Alright, now the next one, here we're given our first term is negative 81. And we're given that, to each term, what are we doing? We're each previous term we're multiplying by negative 1/3. So our second term would be negative 1/3 times 81, right? So how would we write this as an explicit formula? Perfect. So we have our first term, and then we have what we're multiplying each term by, and our n minus 1. So now let's find the sixth term. I heard positive 1/3. One third. All right. We've got lots of confirmation. Good relation error. I'm taking your word on it. So. All right. So questions. We're good with this. All right. So I think we're just about finished. So make sense of problems, revisit the viral video scenario in the beginning of the activity. How many stages will it take until 1 million new people receive the link to the viral video? Explain how you found your answer. So Keisha started it, and she added 3. She added 3 people.
And it was sometime. Yes, I'll just figure it out.
So what was the explicit formula for this one? So we started with 1 person, right? And how many people were multiplied each time? 3. Alright, so for this one, we're kind of working backwards, right? Because we want to know, when is this number going to be 1 million? So when, at what number, 3 to what number gives us something of at least 1 million? So that's I would, because we don't have an operation to undo an exponent, do we? Well, we can. Well, how do we undo a square root? But we don't know what root to take, right? So let's 3 to what number gives us something close to 1 million?
So I got past 1. 15 is too high.
Okay, so at when n equals at stage 12, how many people do we have?
5, 3, 1, 4, 4, 1.
Alright, so that's 500,000 people, right? So that's not enough. Stage 13, how many? 1 million.
5, 4, 3, 2, 3.
3, 2. So we have to get to that 13th stage before 1 million people are added. You know, at this stage, an additional of, and this is really 1.5 million, almost 1.6 that are added. So does it take so long to get, since stage 1 is 1 person? And then, 13 stages later, we're over 1 million people for each stage. Okay, so somewhere in between, in the process of from stage 12 to stage 13. we are going to. So to make this easier, would it have been easier to have been able to just do an operation on to the left side to get an exact instead of trying to guess and check? Spoiler alert, that's what we're going to do. Exponential functions. All right, so